Hello everybody. Today we'll be talking of another consequence of special relativity. So we'll do subtopics in relativistic kinematics. If one recalls, we had to redefine mass. We had this famous mass energy equivalence. Special relativity gives us that. And we also had to redefine mass so as to preserve the conservation of momentum in relativity. And talking of both energy and momentum, how are they related? We know that E is equal to mc square, and then this m, or the total mass of a body, it's actually related with speed at which this body is moving. Okay, so if m0, which you see here, is the rest mass of a body, then if it's moving at a certain velocity v, its mass becomes m divided by root over of 1 minus v square by c square. Okay, fine. And consequently, we also have the momentum defined as the mass multiplied with the velocity, but then the mass again here is velocity dependent. Okay, so how about the relation between them? Why don't we square them up, and if we square the energy and then multiply a c square to the momentum, do a bit of algebra, it turns out, and then we subtract p square c square from the square of the energy. It turns out that we get something which is Lorentz invariant, or in other words, it doesn't change when you change frames, or it doesn't change in frames which are moving with a certain constant velocity with respect to each other. So you actually get m0 c square, and the m0 being the rest mass of your body, and then c square being the velocity of the c being the velocity of light here. Okay, that's pretty interesting. So if we now write it in a certain way, actually if we write all these things in the dimension of momentum square, we get a nice relation like you get a E square, that's the total energy square, divided by the velocity of light square. That gets the dimension of momentum square. That's the linear momentum square that we're talking of here, and then you subtract the momentum which I denote by small p. Okay, you get something which is invariant. Okay, now this I denote by something like the capital P squared. Okay, and just make a comment that still this is momentum squared. That's all. So let's see, is there something behind all these things? Okay, and to check that what is there behind, if you recall what was a 3 momentum squared. Okay, so if you know a 3 momentum square, think of the thing in the Cartesian system, or in any the Cartesian system. So what you see, the 3 momentum squared, you get the x component square, the y component square, and the z component square, or component 1, 2, 3 squared each. Then you add them up, you get an invariant quantity. And you all know that this momentum is a vector, it has 3 components. Similarly, the thing that we talk of when we talk of a 4 momentum, we can also talk of something called a 4 momentum squared. And then what do we get? And if we define the dot product we define a dot product for the case of a 4 momentum as the initial, the 0th component, we call one of the component, the first component with 0th component, and the other 3 components which are equivalent to the usual the vector in the 3 dimension that we all know of. And then we define the 4 momentum, the square of the 4 momentum, with the help of the special dot product. That's why when I say a dot product, I don't put a simple dot, but a rather bigger dot. Okay, so that's equal to actually p0 square minus the 3 dot product of the momentum, the linear momentum that is here, what we have here. Okay. Now, why do we call it as the four momentum? More of it a little later. But here what we see is that if we identify this P0 of the 0th component of the four momentum as E by C, and then the other three components as the linear momentum itself, then what we get is the dot product of this this four momentum dot product shown by P, capital P dot, capital P, is still an invariant quantity. Okay. Now, the notation that I'll be using is for a small p, it will always be the three momentum. If I put a vector, you also know that it's a three momentum vector. But for a four momentum vector, I'll not put any vectors on top of it, and not only that, I'll always use capital letters for it. So capital P is the four momentum, and then the small p is the three momentum that we talk of here. But it's also interesting that we know that the three momentum square, that's an invariant quantity. Okay, you know the dot product, or when you take the square of a vector, you get the length of a vector, which is scalar. So that's an invariant quantity. Similarly, what we see here is that when we take the dot product of the four momentum with itself, we also get an invariant quantity. Okay, that's something to think about. Okay. Now, let's recall a few more things about the four momentum, which we may have covered earlier, but given today's topic of relativistic kinematics, I thought it would be useful for us to review a bit of the four momentum formalism again a bit. Okay. Okay. So just to recall, we can also think of the relativistic phenomenon in Minkowski space-time, okay, where an event is given by an event, or a world point is specified by four quantities, three space quantities, one time coordinate. Okay, of course, you can multiply the constant velocity of light to time, so that you have the dimension of length for all the coordinates. Okay, and then that's what we do. We can simply multiply c to the time coordinate, and then we have x, y, z, let's say. So the three space coordinates, and then we have the same dimension for all, and then we can simply write x0 to be the 0th component, and the other three components for the other three three vector here. Okay. Now, it's also interesting when I take the squared norm, or then the four dot product of x with itself, I'll get c squared t square minus x dot x, like the four dot product we had done earlier for the momentum. And how does the components change when we go from one system to another? Let's say we go from the S frame, where you have the coordinates ct at a certain time, and then x, y, z, and then the same event, if it's measured with the help of from S prime frame, and then you think of that frame as and you measure it at a certain time t prime and x prime, y prime, and z prime. Of course, you now know that these are related by Lorentz transformations. Okay, so the components of this four vector is actually related by Lorentz transformations, which we have covered earlier. And it's actually okay. Just to recall, let's read the first line. So it's the how is the x component in the S prime frame related with the x component with the S frame? You see that x prime is actually equal to gamma times x minus beta ct. Okay, so where beta is the velocity with which the S prime frame is moving divided by the speed of light. Okay, and then the gamma which you see here is nothing but the 1 by the square root of 1 minus beta squared. Okay. Okay, so what's also interesting is that if one takes the four dot product, okay, the four dot product in the S frame and the S prime frame, can easily check that its norm is equal. Okay, that's again something we keep in mind. It's that the norm of a 4 vector is becoming what we check is for this is becoming invariant when is actually invariant when you go from one frame to another. Okay. Now, just as an aside, we can also recall that the norm of a 3 vector is also invariant when you change frames. Okay. Okay. So, to make things a little bit more general, we call all quantities, or rather all quantities which has 4 sets of numbers here. Now, and if they transform, and if they transform in the same way as Lorentz transformations, and not only that, that the squared norm of such a quantity A is becomes same whether you are in S frame or the S prime frame, then such a thing are actually 4 vectors. Okay, and to summarize, what we have is that we have if A is a 4 vector in S frame, then in the S prime frame, the same 4 vector will have, of course, the same norm, but its components will change. Okay, but the components will change in accordance with what? With accordance with the Lorentz transformations. Okay, so that's what we have. The components of a 4 vector will change. The components are related by the Lorentz transformations, and then the norm is invariant. Fine. So, just to put things in perspective again, if we talk of a 4 vector, the momentum 4 vector here, okay, so the 0th component is E by C, that's the energy by C, and then Px, Py, Pz are the other 3 components. Then in the S prime frame, which is moving with a certain constant velocity v with respect to the S frame, the components will be different. Okay, of course it will be different, but the norms of the 4 vectors would be the same. Okay, so now, just as an aside, why do we call it as a 4 vector? Okay, recall what we have in a 3-dimensional space. Okay, so when we have a vector, so what is a vector? So if we recall what a vector is, it's actually that mathematical physical entity which has 3 components here as a 3 vector. That's why it's called a 3 vector. Now, a vector, what's the special property of it? It's that if one changes, goes from one coordinate system to another, now the transformation matrix which one has to use to go from one frame to another, okay, that same transformation matrix is going to change the same vector which is in the old system to the new system. For example, here in this example, if x is a vector in O system and x prime is a vector in the O prime system, see the transformation matrix which is transforming O to O prime will be the same which transforms x to x prime. And not only that, the length of this vector is actually the same. That's a scalar. Okay, so that doesn't change when you change coordinate systems. If you recall what we have just talked of, this quote unquote 4 vector, see some amazing properties which are quite similar with the 3 vector. First of all, it's got 4 components, and then the components of the when you go from one system to another, what is the transformation matrix here? It's the Lorentz transformations. And it's the same Lorentz transformations which is transforming the components of this quantity x or this 4 vector from one system, from one frame to another. And not only that, its norm is fixed. Okay. Okay. So that of course justifies the word, the vector here what you have used, and also it has 4 components. That's why you call it a 4 vector. Okay, so with this, with this background, now I think we can go over to an application. of relativistic kinematics, okay, where let's take a simple example. Let's study two-body collisions. Okay. Now, as in classical mechanics, we can study this in the lab system and also in the center of mass system. Okay. So, what's a lab system? When we consider the collision of two bodies, okay, so the lab system is one in which one of the bodies it has rest and the other comes and hits it. Okay. To keep things simple, I mean, we just take the direction of motion of one of these bodies, of the one which is moving, to be along the x-axis, okay, and it's on a plane, let's say. Okay. Anyway, we also take one of the bodies at rest. So let's just take the body B at rest and the body A, which is coming with a certain linear momentum PA. And if you see, we have also put a subscript L and also a vector. So that's an indication PAL. So that's the indication the P has a vector. So that's a 3 vector, and it's related with the first body A, and then it's in the lab system. So that's the quantity L. That's the reason I put this quantity L. Now, what would be the 4 vector for such a for these bodies? Okay, if recall that the 0th component of the 4 vector relates with the energy. Okay, so we have the energy of particle A or the body A in lab system divided by c, that's the speed of light, and then the other 3 components are the 3 vectors, okay, or the 3 components of a 3 vector. Okay, and what is EAL? So that's nothing but MA into c squared. Okay, that's the mass of A. And then what about PBL? That's the 4 vector PBL. So recall that again it's at rest. So the 3 momentum part of it is 0. Okay, but it's interesting that its energy is not 0. Why? Because of course it has rest mass, and then you have rest mass energy. So you have mb into c square. That will be the rest mass energy. Okay. Now if you take mbc square divided by c, you get mbc, and so you get the 4 vector PBL, that's capital PBL, to be mbc, and then the since the 3 vector part is 0, so we have it 0. Okay. So there's of course another system in which we go over to the center of mass of the system. So all the measurements are being made from the center of mass of the system here, and in this particular case we have the case in which the bodies are moving in such a way that the total linear momentum turns out to be 0 here. Okay. So the same collision process, you're looking at a frame, you're looking in a way in which the both are moving towards each other in such a way that the sum of their linear momenta are 0. Okay. Now it's easy how to write the momentum 4 vectors here for PA. Notice that I haven't used any subscript L here. So except maybe when so only the subscript for the bodies or the particles have been used here. So the other subscript, the CM, is not required. It will be a superfluous thing. So if I don't write it, it means that it's in the center of mass system. Otherwise, it's assumed that it's in the lab system when I write it by this letter L. So the 4 momentum PA, that's the 0th component, we know that's EA by C. Again, all quantities in the center of mass system, and then the 3 vector, that's the PA, and then for the capital PB, that's the 4 momentum for the particle B, that's EB by C, and then it's got a 3 momentum PP. Okay. So how are they related with each other? Remember, so the center of mass system can be thought to be moving with a certain constant velocity v with respect to the lab system. And then if our incident direction of collision is the x-axis, so we just written the S frame and the S prime frame. We just renamed them as L and L frame. That's the lab frame and the center of mass frame respectively here. So in the lab frame, notice that the particle B or the body B is at rest, and the particle A is coming towards it with a certain momentum, velocity, and certain energy here. Okay, kinetic energy, I mean. Of course, for particle B here in the lab system, although it doesn't, you might recall that it has some energy which is associated with the rest mass energy. And then in the center of mass frame, what we have? We have the particles moving with momenta towards each other, equal momenta, so that they are oppositely directed, and when you add them up, they cancel out. Okay. So how are the things related with each other? Recall that the coordinates in the lab and the center of mass frame, they are Lorentz frames here, so they are related by the Lorentz transformations. Okay, and what about the components of the 4 vector of the 4 momentum? So since it's also a 4 vector momentum, we are talking of the components of a momentum 4 vector. The components will transform according to Lorentz transformation itself. Okay, so it's interesting that it's very easy. You can find out if the momentum of any particle is one of them in the lab frame. And the other frame, that's in the center of mass frame, which is moving with a constant relative velocity with respect to the lab frame. You can simply find it out by the help of Lorentz transformation. That's the relation between the lab and the center of mass momenta, and of course the energy being the 0th component here. Okay, it's simple here. For example, if Px is the momentum in the small px, that's the linear momentum along the x-axis in the center of mass system, and then E is just the energy in the center of mass system. Then the Pxl, that's the x component of the momentum in the lab system, is related with the help of Lorentz transformation. That's gamma times Px plus beta E by C. Okay. So it's just the and then since it's we have taken the motion to be along x-axis, so the y and the z components are the same here. Okay. And what about the energy part? Remember, this is the remember this transforms like the time-like components or the CT component when we are doing the position for vector. Okay, so what's the energy in the lab system? So that's simply related with the energy in the center of mass system by, if EL is the energy in the lab system, EL by C, that's actually equal to gamma times E by C. So E being the energy of the center of mass system, plus beta times Px, Px being the x component of the 3 momentum in the center of mass system. Okay, fine. So what's this velocity then with which the center of mass is moving with respect to the lab? Okay, what's this velocity? How can we estimate it? With the help of known components, with the help of known quantities like the mass of the particles in the lab system and the linear momentum of the particles in the lab system. Okay, so let's find it out. And to do that, what we can do is that we can simply apply the conservation of a linear momentum and conservation of momentum and also conservation of energy. And we'll simply take them out from there, okay, by adding the corresponding quantities for these 2 particles. Okay, okay. So first, let's do the momentum conservation first for the momentum for both these particles. Okay, and what we find is that if we add these 2 quantities in the lab system, and then of course we relate them to what these quantities are in the center of mass system. So what we see is that we add PA x, that's the x component in the lab system for particle A, and PB XL, that's the That's the x component of the second particle B in the lab system. By the way, remember that it's actually 0, that the x component that the momentum of particle B is 0. So PB XL, that's actually 0. Okay, so that's equal to gamma times PA plus PB plus beta times EA plus EB by C. Now PA plus PB, so that's 0 in the center of mass frame, and then the energies EA plus EB, how are they related? Let's simply call them as the total energy in the center of mass frame. Okay, in that case we get a rather simple looking relation which relates the momentum of A, that's PA XL in the lab system, with the total energy in the center of mass system. And remember, what is this beta? Beta is nothing but velocity with which the center of mass frame is moving divided by the velocity of light. And then gamma is another kinematical quantity related with beta. And then the C here is the velocity of light, okay, or the speed of light if you wish. Again, from energy conservation, we simply add up the energies in the lab system and then you equate that with the corresponding quantities, with the corresponding expressions in the center of mass system. And we simply also use the quantity that the total momentum, the linear momentum in the center of mass system is 0. Then we also get a rather interesting quantity. Okay, what is it? That the total energy in the center of mass system and the total energy in the lab system, how are they related? Okay, you simply take it out from this relation. But again, from the conservation of momentum, we've seen that the total energy in the center of mass system can be related with the total momentum in the lab system. Now we can use that relation again to drive out some other quantities here, and then from these two equations, the one which relates the total center of mass and the lab energies, and then the one which relates the total center of mass energies with the lab momentum of particle A, we can find out what the velocity with which the center of mass frame is moving with respect to the lab system. You can simply work out that it's nothing but c squared times times the momentum of the particle A divided by the total energy with which the particle A is moving plus the rest mass energy of particle B. Okay, so you have everything with respect to, in terms of everything that you started with, in terms of all lab system quantities. Okay, so what about the collision process? We've not used the 4 vectors as yet. Okay, we've just used the conservation of linear momentum and the conservation of energy separately, and we found out this velocity. Now, what if we use the conservation of the 4 momenta in the lab and the center of mass system? So what do we get from there? Okay, so for that, let's simply add up the 4 momentum of particle A and particle B and take its norm in the center of mass system. And remember that the sum of these 4 vectors is also a 4 vector, and then if you take a norm of that, it's going to be invariant whether you are in the lab system or the center of mass system. Let's simply call this norm as small s, and given that it's still a 4 vector, you add 2 4 vectors, you get a 4 vector, and take its norm. It's Lorentz invariant. So s here is a Lorentz invariant quantity. Then what is it? It's the norm of PA squared. It's the norm of PA, and it's the norm of PB. These are the 4 vector norms plus the 4 vector dot product, twice the 4 vector dot product of PA and PB. Now we all know how to do these 4 vector dot products and calculate these norms, And for example, what's PA squared? That's the 4 vector of A squared in center of mass system. We know that it's also it's EA squared by C squared. That's the energy of particle A in the center of mass system minus the 3 vector norm of particle A. And then the norm of the 4 vector is nothing but MA squared into C squared. That's the rest mass energy squared of that's the rest mass square of particle A multiplied by C square. Similarly, you can find the PB square. That's the norm of the vector, the 4 vector for particle B, and then you can also find the 4 vector dot product of PA and PB. That's nothing but the product of the energies minus the 3 vector dot product of PA and PB. That's a bit of an algebra. Now, when you arrange all these things, plug it back into the expression for S, okay, what you get is that the sum of the total center of mass energy squared divided by C square minus the PA plus PB whole squared, okay. Now, if you recall that the total momenta, the three momenta, when you add these two up in the center of mass system, so that's 0, okay. So, the total energy in the center of mass system, which is EA plus EB, is a Lorentz invariant quantity here, okay, and if you remove the squared here, and you see that it's actually equal to C times root S. Okay, so S being a Lorentz invariant quantity. Okay, so that's a rather important relation we have got here. It's that the total center of mass energy for this two body collision that we see here is actually a Lorentz invariant quantity. Okay, fine. Now, S again is a Lorentz invariant quantity, so we can also find the thing in the lap system. Okay, so we do the thing in the lap system, we take the sum of the 4 vector in the lap system of particle A and particle B and take its norm, okay. Then do the algebra again, so we have PA, L stands for the subscript L is telling us that it's in the lap system, PAL squared plus PBL squared, and then twice PAL dot PBL, okay. So that's the 4 vector dot product. Now, if we use the norm of the 4 vectors being invariant here, so we know that the norms, and we also use the algebraic expression for the 4 vector dot products. Also remember that the and in using the and in writing the 4 vector dot product, we just remember that the momentum of the second particle here B was 0. So, we are not going to have the 3 momentum part here in the 4 momentum dot product, and then the energy of the particle B in the lap system is just the rest mass energy. So, we plug in all these things into the expression for the invariant S. What we get is a quantity which is in terms of the masses and the energies of and then the energy, the initial energy of particle A in the lap system, okay. Just as an aside, what's the kinetic energy of particle A in the lap system? It's just the you subtract the subtract the rest mass energy from EAL, that's the total energy, and you can write the invariant quantity S in terms of the kinetic energy also, okay. Also, we can use a approximation when you are at rather very high energies, things called the ultra relativistic cases, when the momentum is actually much greater than ma times c. That's the rest mass times the velocity of light, okay. If it's rather very big, then how does this expression for the invariant S turn out to be? And in that case, you know that the energy of the total energy of particle A in the lab system is nothing but PAL. That's the momentum in the lab system times the velocity of light. It can be approximated by that, because the other quantity, that's the quantity which depends on the rest mass, will be much less compared to this. Okay. We might do an example for this to check it out whether that's valid or not. Okay. So in that case, we can simply write that the total invariant S in terms of just the lab system momentum for an ultra relativistic case. Okay. We also know that the invariant S that we have defined here, that we have got here, can be written in terms of the center of mass quantities. Remember, the total energy squared divided by c squared, that's also an invariant quantity. Actually, that was also S. Okay. So in this way, we can relate the quantities in the center of mass system, the total energy in the center of mass system, with the total momentum in the three momentum in the lab system. So in a way, it's a method for us to check if you're giving this much amount of momentum in the lab system, how much of it goes to the total energy in the center of mass system. Okay. Okay. So as I said, let's do a small example. Okay. So here, let's consider the collision of two subatomic particles. Let's say we consider the collision of two particles, and then of rest masses. You know, the rest mass of a proton is something like 938, 940 MeV by c squared, but it's approximately, let's take it as 1 GeV by c squared. Now, and then we consider the collision of this in the center of mass system with three momenta of magnitude 30 GeV by c. Okay, this is actually rather very big. Okay, so here you can look at this figure. For example, you see that we have these two protons A and B. They are coming towards each other with momenta 30 GeV by c. Now the question is, what's the linear momentum? What's the momentum in the lab system, which will be necessary so that you have this much amount of momenta in the center of mass system? Okay. Okay. So we simply let's find the center of mass energy of the protons first. Okay. Now it will be, of course, the same. The center of mass energies of both these protons can be found by simply, you know, Pa squared and c squared plus mp squared c to the power 4, and then you take the whole thing to the power half. Okay. So what is that? So Pa squared c squared, what is that? That's 900, 30 squared. Okay. Now to 900, if you add 1, that's the rest mass energies squared. Okay. It's nothing. 900 becomes simply 901. So if you take the square root of 900 or 901, it's approximately 30. Okay. So it's actually an ultra relativistic case that we're talking here. So we can neglect the rest mass compared to the momenta here. Okay. Or rather, rest mass times the velocity of light compared to the momenta here. Okay. Now we also we need to calculate what's the momenta in the lab system. Okay. So for that, let's calculate the invariant Lorentz invariant quantity S. We know that that's related with the total center of mass energy squared, right? So S will be 30 plus 30 here, because each of these protons have total energies 30 in the center of mass system. So S is nothing but 3600 GeV squared by c squared. Fine. We can also relate this with we have seen how it's related with the lab system momenta. Okay, that's actually equal to twice the mass of the protons times the velocity of light times the linear momenta. Okay. Now if you plug in all these quantities, you will get the linear momenta of in the lab system to be 1800 GeV by c, which is huge. Okay, which is rather huge. So you see, to get energy of 30 GeV per C, you need such a huge momenta in the lab system, okay? And this also, and then this number actually justifies the approximations that we have used, that of our ultra-relativistic case, in which the momenta was considered to be was much larger than the rest mass times the velocity of light here in this case. Okay, so I hope I have convinced, I have shown you some examples of relativistic kinematics, more specifically relativistic collisions, and the use of the four momentum, or the power of the use of four momenta in relativistic kinematics. Thank you very much.